All right, so 4.4. The title of this section is the mean value theorem. And, we were talking earlier about this idea that some of us have trig trauma, or we see, domain, and we're like, oh my gosh, I never knew what that was. And I think another trigger word is this word theorem. But all it means is it's like something that is always true. Okay. And if you think about it that way, there's so few things in our life that are always true that it's kind of cool that we have all of these things in math that are always true. Okay. And so what we're looking for is not just like sometimes this happens and sometimes that happens, but if we have a very special set of circumstances, we're going to be able to guarantee something. Okay. And turns out, I think that especially this group, we've done such a good job rooting ourselves in the pictures and like what it means to have slope and y values. I think this section actually will make a lot of sense to us. It's just dressed up in some math language that we want to now embrace and say, oh, okay, I get what this means. All right. So let's get started. What do we know? Well, we just talked about extrema, what they are, how to find them. We're going to get more in depth into how we find our extrema in 4.5. Okay, so let's go ahead and put a note right here that we're going to see more of this in 4.5. All right. We also talked a little bit about Fermat's theorem in the previous lesson. And the basic gist of it was if you have an extrema and you also have a smooth curve, no surprise, shocking transitions, right? Just extrema and differentiability, then what's going to happen is that point will have a horizontal tangent line. All right. So if something has an extrema and it's differentiable, then you are always guaranteed to have the horizontal tangent equal to 0. Or rather, the horizontal tangent or the slope at that point is going to be equal to 0. And so what's new in this section? Well, we're going to be talking about two theorems in particular. We're going to talk about the mean value theorem, and then we're going to talk about Rolle's theorem. All right. And before we start crying about how we're actually learning two theorems and not one theorem, I do want to put it out there that Rolle's theorem is nothing more than a special case of the mean value theorem. Okay. So even though it's 2, if we get the mean value theorem, then Rolle's theorem actually, I think, makes a lot of sense for us. Okay. All right. So let's take a look at some pictures. My favorite. I did take one class this past semester where there were no pictures, and I was like, but I don't even understand how I'm supposed to do this. So I think I find a lot of joy in finding the pictures, and it can be very hard for me if we don't have them. But let's take a look at these 3 graphs. Okay, so we've got an A, a B, and a C. And I'm wondering if we can unpack what is the same about these graphs, and then separately, what is different. Okay, so as specific as we can be. Okay, so being specific, what are some things that you notice about the graphs that are the same? Okay. All right, so we've got the domain of A is the domain of B. All right. And so we can tell the domain by seeing like we start at A and we end at B. All right, we start at A, we end at B. Could we say the same for C? Does it start at A and end at B? Yeah, okay. So I like that in terms of thinking about the concept, maybe something that is the same. Let's start listing these out. We've got domain of all three is A to B, and I'm going to use square brackets. I'm going to use square brackets so that I know I'm including A and I'm including B. Okay. All right. They all have extrema and they're all differentiable. Check out that language, right? I know we just learned this, but the more that we practice this kind of language, even if it feels awkward to us at first, the more you're making that language stick in your brain. Okay. So you're right. In all three of these pictures, they have extrema. All right. So all have extrema and are differentiable. Everything is nice and smooth. No birds from elementary school drawings. No sudden changes in behavior, right? Everything is nice and smooth. Things sort of change in a predictable manner, right? Anything else? Anything else that we notice might be the same between all three graphs? Question, what is the lower horizontal line on A supposed to be showing? Ah, are you talking about this? Ah, okay. So let's unpack that a little bit. What is the coordinate of that pink point? Yeah, it's A for the X value. And then maybe we could say that it is F of A for the output. Exactly, exactly. Okay. Now, tell me the coordinate of this green point. Right, right. B, F of B, right? What can we say about the pink point and the green point? Bingo. That horizontal line is telling us that those Y values are equal. Exactly. They are also the endpoints of this graph for sure. But one thing that we might notice is that F of A equals F of B, right? Let's check and see, is that the same on graph B? I say this is a pink point and this is the green point. Yeah, we can say again that F of B is the same as F of A. All right, let's check that third graph. A, F of A, B, F of B. In all three graphs, F of A equals F of B. Okay, and that is super important to connect to the fact that they are the endpoints of the domain. All right, they are the endpoints of the domain. All right, so those are all the similarities. What are some things that are different? What are some things that are different about these graphs? Yeah, the degree, right? Like the first two, they only have one bump. But the second or the third graph, that has two bumps. right? So they're facing different directions. Some have one bump, others have two. Yeah. Okay. Now here's the cool part. Despite these differences, it turns out that what really is going to matter is the things that are the same. Okay. And I think that is one of the hardest things about wrapping your mind around a theorem, is that some things must be the same in order for this theorem to be true. Other things can actually be different and it doesn't actually matter. Okay. So it's not that everything has to be exactly the same, it's that certain features have to be the same. All right. So we're going to come back to this, but I want to leave this for right now. And we're going to take a look at a different picture. All right. And looking at this picture, I'm wondering if we can rewind our brains. Luckily, we're in a summer session, so we have less time to rewind, but it's been very intense, so maybe it's harder to sift through all the information. But what concepts or formulas does this particular graph remind you of? Something that we learned, I forget which week it was, week 1, week 2. All right, average rate of change, instantaneous rate of change, yeah. So if we take a look at this line right here, all right, one of the reasons that I have been sort of asking us about average rate of change a lot, right? This is our average rate of change. We can also call it that secant line. And then we have this other line hanging out here. And this one we describe as our instantaneous rate of change, or maybe our tangent line, right? And yeah, it does kind of look like that formal definition of the derivative. Like if A and B were super close together, then we would have our formal definition picture, right? But what can you tell me about the average rate of change and the instantaneous rate of change in this case? They appear to be equal. And yes, that is the goal of this diagram, is that these two lines, the blue one and the orange one, should look parallel to each other, or rather they should be equal in slope. Okay. And so one way for us to represent that is that the instantaneous rate of change equals the average rate of change. Okay. How can I say instantaneous rate of change at x equals c? How do I say that in notation? Okay, I can say f prime of c, and that is the same thing as saying my instantaneous rate of change at c. Okay, so these two both represent the slope of that tangent line, all right? In contrast, how would we describe the average rate of change? In terms of a formula, how would we write average rate of change? Yeah, this is our throwback to like middle school when we first learned about slope, right? And so let's use our f of b minus f of a over b minus a. to describe that average rate of change. Now, the reason why we typically have the F notation instead of the Y notation is just because it's a little bit more precise. It tells us exactly where those 2 points are that you're finding that average rate of change for, okay? All right. So knowing these things, let's talk about Rolle's theorem first, which is the special case, and then we'll talk about the mean value theorem, which is the more general case, okay? All right, so this is not how a textbook would present it, but it is one way that, especially if you're like moving on to Calc 2 or Calc 3, if you read a theorem and you can say, these are the things that have to be true, and from that, this is what I know, sometimes that vertical division helps my brain understand a little bit more clearly what I'm trying to unpack from the theorem. Okay, so that might be a tool that you find useful. And if not, you can use the textbook definition, that's fine. All right, but Rolle's theorem says that there are 3 things that have to be true. Okay, first, they want the function to be continuous over some interval. Okay, so if we want to know if Rolle's theorem works, the very first thing we have to check is that function continuous? Okay. The second thing that we need to check is f is, here's that word again, smooth, differentiable over, but here's the catch, it's not inclusive. Okay, because sometimes at the end points, we end up with pieces that might be sort of sharp, or we don't know what happens on the other side. And so we just want to say in the interval we're looking, but don't worry about the endpoints, that the function is differentiable. The third thing that has to be true is the pattern that you all noticed as soon as Luca asked that question, what is that horizontal line on the bottom? And here's the third piece, the third clue you need to look for. F of A, the Y value at one end, is equal to the Y value at the other end. In other words, we can use Rolle's theorem if these things are true, or the picture we might have in our brain is any one of these pictures. If you have a picture that looks like this, then there's going to be one thing that is true, guaranteed every single time. Okay. Here's the thing that is true. If a function is continuous and it's differentiable, yes, all 3 of these have to be true. Okay, this is the tricky thing about theorems, because we're going to be writing down something that's always going to be true. It's so hard to find something that's always true that we need to have a very specific set of circumstances for that to happen. Okay, so here's what we know. All right, there exists at least one. All right, so only, it has to be at least one, but it could be more than that, right? I think Matt noticed that there was like a first or second degree, a third degree. And when we talked about that in terms of bumps, some of the graphs had 2 bumps. One of the graphs had, 2 of the graphs had 1 bump. One of the graphs had 2 bumps, all right? So there exists at least one X value that we're going to call C, such that C is between A and B. all right? I know that's not alphabetical. You know that's not alphabetical. We sort of set the endpoints first. That's why we have A and B. Then we want to describe the one in between them. So then we come back and use the third letter, C. Okay, so there exists at least one X value C such that C is between A and B. And you know what else is true? F prime of C is going to equal 0. All right. So if we can say F is continuous, F is differentiable, F of A equals F of B, then every single time we know there's going to be at least one extrema in that interval. Okay. I think it's really easy to get on your high horse as a mathematician and be like, obviously this makes sense, right? But I think also being in some classes that are hard, it brings a lot of this idea that there are ways to explain things, that it doesn't have to be as challenging, right? But I think what might be useful is if we take a look at 2 examples, how we actually apply this theorem. And thinking about what we know about graphs, all right? So like earlier we learned, or we remembered that polynomials are always continuous. If we have a fraction, we should always check that denominator to see if it's not continuous, right? And so that might be something that we sort of think about as we approach these kinds of problems. All right, so example 1, verify that the function f of x equals x cubed minus 4x over the interval -2 to 2 satisfies Rolle's theorem, and find all values of c such that f prime of c equals 0. All right, so the first half is saying, tell me that you know Rolle's theorem is going to be applicable here. The second part, this finding the values of C, is saying, now I want you to find where those horizontal tangents are happening. Okay. So let's I never know the best way to do this. So can I do a new share? I've not done this without switching out of this. So can you see a different screen now? And do you only see one screen? Okay, cool. All right, so we have Desmos here. I have used our friend Desmos to graph this function, right? And I noticed that it is a cubic function. And in particular, we might notice that we have a local maximum right here and a local minimum down here, all right? According to the graph, what x values do those, what x values do those seem to be? Yeah, -1 and +1, right? And if we clear this for a moment, I'm gonna zoom, oh, no. All right. Thanks for not judging me. All right, if we zoom in a little closer though, we might see that it's actually not quite at 1 and not quite at -1, right? It's like a little bit larger than +1, a little bit less than -1, all right? But we're sort of in the ballpark. So we know we should have 2, all right? And let's think about where our interval is. Our interval starts here at -2 and goes to +2, all right? So from the graph, is this function continuous? Yeah. is this function differentiable? Right? It is nice and smooth, no sharp turns, right? Is f of b equal to f of a? Sure is, right? Both stars are right on the x-axis, meaning they both have a y value of 0. Okay, so let's keep that in mind. Let's come back and let's do the algebraic way. All right, so let me exit out of my, let me clear these. Let me exit out of the annotation and let's reshare the original. Okay, so sorry. Okay. All right, so we know from a graph that it satisfies Rolle's theorem, but how do we show that without a graph? We can say a few things. F of x is a polynomial. Therefore, f of x is continuous and differentiable over -2 to 2. So f of x is a polynomial, therefore f of x is continuous and differentiable over the interval. And in fact, it is actually continuous and differentiable over all real numbers. We're not concerned about those because we're looking at a specific interval right now, but you could also say that it's continuous and differentiable over all real numbers. Okay. So that satisfies the first 2 points. It is continuous, it is differentiable. How do we show that f of a equals f of b? How do we show that using algebra and numbers? Yeah, we plug in the x values, right? So let's grab our function. We're going to plug in -2. We're going to see what we get. We're going to grab our function. We're going to plug in +2, and we're going to see what we get. All right. So I have -2 cubed. Wow, that's a 3. 3 minus 4 times -2. And then 2 cubed minus 4 times 2. Always a good always a good chance to practice our positive and negative signs, keep that mental math fresh. Though I will tell you quite honestly, the more math I do, the more math I learn, the more terrible my computation gets. I don't know why that is, but I make all sorts of mistakes. So let's just make sure we're all good here. -2 cubed should be -8. And then -4 times -2 gives me a +8. And so I'm getting a y value of 0. And that's good because that matches our graph, right? And if we plug in the other value, which is a +2, 2 cubed is 8, minus 4 times 2 is 8. I also get 0. And so I have shown that f of -2 equals f of +2. All right. And so we have shown that all 3 conditions for Rolle's theorem are true. That's all we need to verify the theorem. You've shown that everything in this left-hand box is true. Now for the second part of the question, we need to find where those values are. And we know that they're pretty close to +1 and -1, but they're not quite there. And so this is actually where algebra is a little bit more powerful than our graphical notation because we can find an exact value more easily. All right. So we're going to find f prime of c. We're going to set that equal to 0. All right. So I'm going to take this function, x cubed minus 4x. I'm going to take the derivative and I'm going to plug in c. So I'm going to get 3c squared minus 4 equals 0. Okay, so I took my derivative, I plugged in c, I got 3c squared minus 4 equals 0. I'm going to go ahead and add 4 to both sides. I'm going to divide by 3. So c squared equals 4 over 3. Last step, take my square root. 4 has a square root. That is a perfect square, so I can write it as 2. 3 does not have a perfect square, so I'll just call that root 3. Okay. This is probably much to the demise of your previous instructors. I don't care if you rationalize this or not. You might find the future instructors that care as much. I do not. But what I do care about, and the reason why I left the gap between the equal sign and the 2 over root 3, is because we want to make sure we know there's not one solution, but there are 2. I don't know how old your previous professors are. I think that a lot of the older instructors that I encounter tend to be very, very like committed to some of the ways that they learn things. Everyone has different things they are picky about. That's why we're all math instructors. Here we are. Okay, but it is more important, I think, that we know there are 2 solutions rather than one, because when we looked at the graph, we ended up with a picture that looked something more like this, meaning here was a value, but here was a second value. All right, so we want to make sure we find all the values, and one of the easiest places to miss one is that plus minus part. Okay. All right. So how are we feeling with this example? Because we've blown through a lot of content today, a lot of like ideas. Okay. Well, I think it's important to be able to solve a question. All right, for sure. Like I want us to know how to do example 1, but I think it's just as important to think about what might make Rolle's theorem not true. Okay. And so maybe this will be a good exercise for us to actually gain a better understanding. Do we know what's going on or do we not? Because if we're able to manipulate things, that shows a different level of understanding than just being able to execute the flow of a problem. Okay. So let's take no more than 5 minutes and kind of think about this. All right. From the question above, what could be changed so that I can't solve? It doesn't even satisfy Rolle's theorem. If I added a denominator, yeah, maybe it would be 0. What's the problem with that? Right? I think what you're saying is very specific. I'm wondering if you could broaden that a little bit. Like, what does having a 0 and a denominator cause to change about our checklist here? It could be undefined. It could have a hole. Exactly. And so if we used sort of fancy language, we could say that we choose a function that is not continuous. For example, maybe the most simple case, if I change the function to 1 over x, that's not continuous anymore. So I cannot use the part of this where it is not continuous. Okay. All right, let's go back to that list. What else could we do to say Rolle's theorem doesn't work here? Okay, and what's the problem with the absolute value, right? Let's generalize that problem. I would agree, and I think that's a great example. Ooh, that's a third point. All right, so let's come back. Let's say that we could also choose a function that is not differentiable. In other words, a good example of this would be like the absolute value of x. Because if we're choosing that interval and we have a pointy value there, we're not going to be able to apply Rolle's theorem. All right, and Joey, you've got it with this last one. We could change the interval so that if we change the interval, what are we hoping is no longer true? Yeah, so if we change the interval so that f of a does not equal f of b, that's also going to tamper with our Rolle's theorem checklist. Okay. And so this sort of like flow here, in some ways it's very specific to Rolle's theorem, and in some ways it's actually a really good framework to think about math in general, right? List out what you know has to be true and what follows from that. And then try doing some application problems like example 1. But this, I think, is such an important conversation to have with yourself or with other people. Or if you feel like you're not sure what questions to ask, even asking a question like, well, when would it not be true? Is a good question to ask. Okay. All right. So let's finish today with the mean value theorem. The mean value theorem, we will approach it in a similar way. We're going to say, if these things are true, then we know that. And I think just from the left-hand side, we'll see that it is a more general case of Rolle's theorem. It turns out that we only need 2 things to be true here. F is continuous over the inclusive interval a to b. And f is differentiable over the open interval a to b. Those are the only things we need to have. We do not need to have f of a equals f of b. All right. So if you've got something that is continuous and differentiable, here's what's going to be true. All right. There exists at least, there's that word again, at least one x value c such that That weird alphabetical thing again. C is between A and B. All right, so there exists at least one value C such that C is between A and B. And the slope at C is equal to the average rate of change. In other words, instantaneous rate of change equals average rate of change. All right. In other words, this picture right here, you folks looked at that picture, you told me, here's my instantaneous range of change, here's my average rate of change, and they appear to be equal. And then we wrote an equation about it. How fancy are you folks? I didn't even tell you what the mean value theorem is, and you looked at a picture and you could be like, yeah, I see that those are the same. And all that time that we worked on, what's another way to write instantaneous rate of change? Bam, useful right here, right? All that time we worked on, what's the average rate of change? And you were able to tell me it's the slope formula, comes in right here. The only thing you needed to tie together was that sometimes those slopes of the instantaneous rate of change and the average rate of change are indeed the same. All right. Now here's the cool part. That picture is going to be true anytime you have a continuous and differentiable function. All right. It's going to be true anytime you have a continuous and differentiable function. All right. So let's draw some pictures. Okay. I have some function here. And I have a tangent line, or sorry, and secant line. And I'm wondering if we have any brave souls who can sketch some tangent lines so that the tangent lines have the same slope as the blue line. Oh no. All right. This is definitely a little tricky because we're thinking, here's my function. I have so many different slopes, but in particular, I want to find a point that might have the same slope. And so maybe one of those points is like somewhere here. Right? So I think maybe I should have drawn that a little bit more to the right, but then that orange line would have the same slope as the blue line. Are any points in this region going to have the same slope as the blue line? What are our thoughts? Yeah. Where in that region? At the higher bump, like over here? Okay, so if I drew a tangent line here, it would look something like that. How do I get a point that has a slope that is exactly like the blue line though? Yeah, maybe a little bit to the right of that, right? So maybe something like right here. Whoa, that is not. Ah, okay. Sometimes we just have one of these days. All right, but roughly in that region, we can kind of see that the slopes of the orange line are the same as the slopes of the blue line, okay? And as long as I draw any continuous and differentiable function, I'm gonna be able to find at least one. All right, so that is pretty cool that you can just have two very small things that are true, continuous and differentiable, and then you're always gonna have slopes of tangent lines that are equal to the slope of the secant line. So let's finish off today with example 4, just so we get a little bit of that practice in the application, all right? So example 4 says, find the x value of all points in the interval 0 to 2 of the function f of x equals x minus 1 to the 18th that satisfy the mean value theorem. All right, we should check first. Does it satisfy? Is it continuous? Is this function continuous? And then secondly, we want to ask ourselves, is this function differential? All right. Now, I would say this should be a quick yes for both of these. Yes, it is continuous. Yes, it is differentiable. Yes, because f of x is a polynomial. All right, so we can use that for free, that we know f of x is a polynomial, so therefore it is continuous and differentiable everywhere. Okay. So how do we find these c values? Well, it turns out that we're gonna grab this formula that we created from our picture that also happens to be this mean value theorem, and we're going to fill in all of the information specific to our function and the given interval. So we have f prime of c equals f of b minus f of a over b minus a. All right. What can I put for the left-hand side? How could we express the left-hand side? Yeah, we could use chain rule, all right? And the only thing we're gonna do, we're gonna take that derivative, and everywhere we see an x, we're gonna plug in a c, all right? So we're gonna get 18 c minus 1 to the 17th times the derivative of the inside is just 1. Okay. Now, what numbers can I plug in for a and b on the right-hand side? Yeah, we can say that B is going to be 2 and that A is going to be 0. Okay, so we want to be really careful here because A is different from f of A and B is different from f of B. And so we might take the step to say f of 2 minus f of 0 over 2 minus 0. That's okay. But we don't have C values here because the C is just for that one point that is in the middle of A and B. Okay. All right, we get 18 C minus 1 to the 17th equals, let's see, f of 2, if I plug 2 into here, 2 minus 1 is 1, and 1 to the 18th is 1. 0, whoops, 0 minus 1 is negative 1. And negative 1 to the 18th is positive 1. All right, so my f of 2 and my f of 0 are actually the same. Divided by b minus a, which is 2. All right. Now, if we simplify this, we get 18 c minus 1 to the 17th equals 0. I can divide both sides by 18. I can take the 17th root. Right, I can take that 17th root. And then I can add 1 to both sides. And it turns out that there is only one place where the slope of the function is going to be the same as the slope between 0 and 2. Okay. So I know we've done a lot today. I would encourage you to marinate on these concepts, practice them sooner rather than later, and definitely ask questions if you're not sure about things, okay? But we don't need to be scared of the word theorem. It's okay for it to be harder than some other things, but I don't think we need to be scared of it, all right? So, yes, go ahead.
Yeah, I have a question for the quiz 9. There's a section from 7 to 10 when we have to select and solve 3 of the 4 questions. If I will do 4, could I able to get an extra credit?
No.
Okay, thank you.
I will grade the first 3 that I see. All right. Well, folks, if you don't have any other questions, have a great rest of your day, and I will see you folks tomorrow.